At first, the universe seems to be made of light. Stars burn, galaxies glow, nebulae scatter color across the dark. Telescopes reveal spirals, clusters, jets, explosions, rings of gas, and ancient radiation stretched across the sky. But when we step back far enough, another universe appears. It is not defined by what shines. It is defined by what does not. On the largest scales we can map, galaxies are not scattered randomly like dust. They gather into a vast, irregular network. Clusters become knots. Galaxies form chains. Chains stretch into filaments. Filaments intersect in walls and sheets. Together they create the cosmic web, the largest known pattern in nature. And between those luminous threads are the voids. Immense regions where galaxies are rare. Regions so large that light itself may need hundreds of millions of years to cross them. Regions that are not truly empty, but are empty enough to shape the architecture of the universe. A cosmic void is not a hole. It is not a tear in space. It is not a place where reality failed to form. A void is a region of the universe with much less matter than average. It contains dark matter, thin gas, radiation, and sometimes faint isolated galaxies. But compared with the crowded filaments and clusters around it, it is a vast cosmic underdensity. If galaxies are the cities of the universe, voids are the wilderness between continents. If clusters are mountains, voids are valleys. If the cosmic web is a skeleton, voids are the spaces that give it shape. The story of the voids begins not in darkness, but in fire. The early universe was hot, dense, and nearly smooth. Nearly. That word matters. If everything had been perfectly smooth, gravity would have had no preferred places to work. Matter would have remained evenly distributed. No stars, no galaxies, no planets, no life, no observers. But the early universe contained tiny differences from place to place. Some regions were slightly denser than average, others were slightly emptier. These variations were extremely small, but gravity is patient. Over time, the denser regions attracted more matter. The emptier regions lost matter to their surroundings. The rich became richer. The poor became poorer. Matter flowed toward matter. Gravity amplified the smallest imbalances. Dense regions became the seeds of galaxy clusters and filaments. Underdense regions became the seeds of voids. This means voids were not carved out later by explosions. They were not blasted open by supernovae. They were not swept clean by some ancient cosmic wind. They grew naturally from the same process that built the galaxies. The universe did not only form structures, it formed absences. For the first hundreds of thousands of years after the Big Bang, the universe was opaque. It was filled with a hot plasma of charged particles and light. Photons could not travel freely because they kept scattering from electrons. Space was bright, but not transparent. Then the universe expanded and cooled. About 80,000 years after the Big Bang, electrons and nuclei combined into neutral atoms. Light could finally move freely through space. That ancient light is still with us today. We call it the cosmic microwave background. It is the oldest light we can observe, a baby picture of the universe. Across that microwave sky are tiny temperature differences, only about 1 part in 100,000. To the eye, if we could see microwaves, the universe would look almost perfectly uniform. But to cosmologists, those tiny variations are everything. They are the fingerprints of the early density field. They show the seeds from which the cosmic web grew. The hot and cold patches in that ancient radiation are not galaxies yet. They are not stars. They are not voids in their modern form, but they are the beginning of the pattern. The future clusters, the future filaments, the future walls, the future emptiness. In those tiny fluctuations, the voids were already waiting. As millions of years passed, dark matter played the leading role. Dark matter does not emit light. It does not shine, reflect, or absorb in ordinary ways. We know it through gravity. It pulls on visible matter, it bends light, it shapes galaxies and clusters. In the early universe, dark matter began clumping before ordinary matter could form stars. It provided the gravitational scaffolding on which galaxies later assembled. Ordinary matter fell into the dark matter structure. Gas cooled. Stars ignited. Galaxies formed. But in the underdense regions, there was less matter to gather, less gravity to collapse, and fewer places where galaxies could easily form. Matter moved away from those regions toward the denser surroundings. The voids expanded relative to the rest of the universe. This is one of the strange truths of cosmic structure. Gravity, the force we think of as pulling things together, also helps make emptiness emptier. If matter flows into dense regions, it must flow out of underdense ones. Voids are not passive gaps. They evolve, they grow. Their edges become sharper as material drains toward walls and filaments. Their interiors become quieter, dimmer, and more isolated. The bright cosmic web and the dark cosmic voids are not separate creations. They are two sides of one gravitational process. For most of human history, we had no way to see this pattern. The night sky showed stars, planets, the Milky Way, and a few faint smudges. Even after telescopes revealed that many smudges were galaxies, the larger arrangement remained hidden. A galaxy's position on the sky gives only 2 dimensions. To see the universe in 3 dimensions, astronomers needed distance. One of the greatest tools for this is redshift. As the universe expands, light traveling through space is stretched. Its wavelength becomes longer. The more space expands during the light's journey, the more the light shifts toward the red end of the spectrum. By measuring this redshift, astronomers can estimate how far away a galaxy is and how long its light has been traveling. With redshifts, galaxies become points in a 3-dimensional map. At first, the maps were small. Then they grew. Survey after survey revealed the same astonishing fact. Galaxies are arranged in an enormous web-like structure with huge regions of relative emptiness between them. The voids had been invisible, not because they were imaginary, but because their scale was too large for ordinary observation. They became visible only when astronomers mapped what surrounded them. One of the early famous examples was the Boötes Void, discovered in the 1980s. It appeared as a vast region with far fewer galaxies than expected. Its size shocked astronomers. The universe was not a smooth fog of galaxies. It contained enormous empty spaces. Yet the Boötes Void is not truly empty. That is essential. Even the emptiest cosmic voids contain something. They contain dark matter. They contain sparse gas. They contain radiation passing through. They may contain faint galaxies that are difficult to detect. A void is not nothingness. It is a place where the density is low compared with the cosmic average. In everyday life, emptiness sounds simple. In cosmology, emptiness has structure. Voids have sizes, shapes, boundaries, histories, and internal features. Some are relatively small, tens of millions of light-years across. Others are much larger. Some are roughly spherical. Others are elongated or irregular, shaped by the surrounding web. Some contain smaller voids inside them. Some merge with neighboring voids over time, forming larger underdense regions. And then there are supervoids. A supervoid is an exceptionally large underdense region. It may be a single vast void, or it may be a connected complex of smaller voids. The word does not always have one perfectly fixed definition, because voids do not come with hard edges. They are identified through the distribution of matter in galaxies. Different surveys and algorithms can define their boundaries differently. This is important. The universe is not labeled. It does not draw lines around its structures for us. A galaxy cluster is relatively easy to point to. A void is more subtle. Where does it begin? Where does it end? How empty must it be to count? When do several connected voids become one supervoid? These questions are not just technical details, they are part of the science. When astronomers talk about the largest voids or supervoids, they are speaking about structures identified statistically in a continuous cosmic density field. A supervoid is not a bubble wall around absolute nothing. It is a vast region where matter is missing compared with expectation. And that missing matter may be one of the most powerful clues we have. To understand why voids matter, imagine the universe as a landscape. The dense regions are peaks. Galaxy clusters are the highest mountains. Filaments are ridges. Walls are broad, elevated plains. Voids are valleys and basins. A landscape is defined not only by mountains, but by the spaces between them. Without valleys, mountains have no shape. Without voids, the cosmic web has no structure. Voids are also cosmic laboratories. In dense regions, the universe is complicated. Galaxies collide. Gas is stripped away. Star formation is triggered or shut down. Supermassive black holes feed. Clusters heat gas to millions of degrees. Gravitational interactions are constant. Inside voids, the environment is quieter. Galaxies that live there are more isolated. Many are smaller, bluer, and more actively forming stars than galaxies in crowded regions. They have fewer close neighbors and fewer disruptive interactions. Their evolution can be slower, cleaner, and more influenced by internal processes than by violent encounters. A void galaxy is not alone in an absolute sense. But compared with a galaxy in a cluster, it lives in solitude. This makes void galaxies valuable. They help astronomers ask how environment shapes galaxy evolution. What happens to a galaxy when it grows far from the cosmic cities? How important are mergers? How important is gas supply? How different is a galaxy's life when it is born in the quiet interior of a void? Voids help separate nature from nurture on a cosmic scale. They also reveal the hidden role of dark matter. Although we see galaxies, the cosmic web is not made only of visible objects. Dark matter forms much of the gravitational structure. Voids are underdense in ordinary matter and dark matter. The galaxies trace the pattern, but imperfectly. The true cosmic web is made of all matter, seen and unseen. How do we study invisible matter in an empty region? One way is gravitational lensing. Einstein's general relativity tells us that matter curves space-time. Light follows the curves. When light from distant galaxies passes through regions with mass, its path bends slightly. Massive galaxy clusters can create dramatic arcs and multiple images. But weak lensing is subtler. It slightly distorts the apparent shapes of many background galaxies. A void produces a weak lensing signal too, but in a different way from a cluster. Because it contains less matter than average, it changes the light path according to its underdensity. A single void signal is faint. But by stacking many voids together statistically, astronomers can detect the imprint of missing mass. This is one of the most poetic facts in modern astronomy. We can measure emptiness by the way it bends light, and through that bending, voids become probes of gravity. They are not merely gaps in the galaxy distribution. They are tests of the laws that govern the universe. Because voids are low-density environments, they may be especially useful for testing whether gravity behaves exactly as general relativity predicts on the largest scales. General relativity has been extraordinarily successful. It explains the orbit of Mercury, the bending of starlight, gravitational waves, black holes, and the expansion of the universe when combined with the observed cosmic ingredients. But the universe is accelerating. We call the cause dark energy, though we do not know its true nature. In the standard model of cosmology, dark energy is often represented by the cosmological constant, a constant energy of space itself. This model, called lambda cold dark matter, or lambda CDM, describes a universe containing ordinary matter, cold dark matter, radiation, and dark energy. It works remarkably well. It explains the cosmic microwave background. It explains the growth of large-scale structure. It explains the broad distribution of galaxies. It explains why the universe looks almost the same in every direction on the largest scales. But it is not the final word. Dark matter has not been directly identified as a particle. Dark energy remains mysterious. Some measurements of the expansion rate of the universe do not agree as well as they should. Some large-scale features of the cosmic microwave background remain debated. Voids enter these mysteries because they are sensitive to expansion, gravity, and the growth of structure. A void expands faster than the cosmic average around it, not because space inside it has a separate Big Bang, but because there is less matter inside to slow expansion through gravity. Compared with denser regions, voids grow. Their interiors become emptier as matter flows outward towards surrounding filaments and walls. That outflow can be measured through the motions of galaxies. Galaxies move because the universe expands, but they also have peculiar velocities caused by local gravity. Around a void, galaxies tend to move away from the underdense center and toward denser structures. When astronomers infer distance from redshift, these motions distort the apparent shape of the void. This is called redshift space distortion. By studying those distortions, scientists can test how fast structure grows and how gravity behaves. If gravity is modified on cosmic scales, voids may reveal it. If dark energy changes over time, voids may help show it. If the standard model is incomplete, voids may be one of the places where the cracks become visible. This is why modern surveys matter so much. The Sloan Digital Sky Survey mapped galaxies across enormous volumes and helped reveal the cosmic web with unprecedented clarity. The Dark Energy Survey studied hundreds of millions of galaxies, supernovae, galaxy clusters, and weak lensing patterns. DESI, the Dark Energy Spectroscopic Instrument, has built one of the largest three-dimensional maps of galaxies and quasars ever made. ESA's Euclid mission is designed to map billions of galaxies across more than a third of the sky and explore how structure formed over cosmic history. The Vera C. Rubin Observatory will repeatedly scan the sky, building an immense record of changing and distant objects. These surveys turn the universe into data, and in that data, voids become measurable. Their abundance can be counted, their shapes can be compared, their galaxy populations can be studied, their lensing signals can be stacked, their motions can test gravity. Their relationship to cosmic expansion can test dark energy. The empty places are becoming precision tools. To appreciate their scale, we must leave human distance behind. Light travels nearly 300,000 kilometers every second. In 1 year, it crosses almost 9.5 trillion kilometers. The nearest star system to the Sun is more than 4 light-years away. The Milky Way is about 100,000 light-years across. The Andromeda Galaxy is about 2.5 million light-years away. A large cosmic void can be hundreds of millions of light-years across. A supervoid can be larger still. If the Milky Way were placed deep inside one of the largest voids, the nearest major galaxies might be so distant and faint that early astronomers on an Earth-like planet could have imagined a much smaller universe. Their sky might have contained stars, nebulae, and perhaps a few faint galaxies, but the larger cosmic web would have been far harder to discover. Our own location is not in the center of a giant empty void. We live in a galaxy that belongs to the local group, near the edge of the local void and within the broader structure of nearby groups, filaments, and superclusters. Our cosmic neighborhood is neither the densest nor the emptiest place. It is part of the web. But the possibility of local underdensities matters. Some scientists have asked whether our region of the universe could be less dense than average on very large scales. Such a local void could slightly influence local measurements of cosmic expansion. This idea has been discussed in relation to the Hubble tension. The Hubble tension is one of the most important open problems in modern cosmology. Different methods of measuring the present expansion rate of the universe give different answers. Measurements based on the early universe, especially the cosmic microwave background interpreted through lambda CDM, tend to give one value. Measurements based on nearby distance indicators, such as Cepheid stars and Type Ia supernovae, tend to give a higher value. Could a local void explain the difference? Maybe it contributes a small effect. Local structure certainly matters. Galaxies do not simply ride the smooth expansion of the universe. They are pulled by nearby clusters, pushed relative to underdensities, and affected by the uneven distribution of matter. Astronomers must correct for these motions. But most studies do not find that a local void alone can fully solve the Hubble tension. The disagreement may come from hidden measurement systematics. It may require new physics. It may involve dark energy, neutrinos, early universe effects, or something not yet imagined. Voids are part of the investigation, but they are not a simple answer. That is often how science works. The most interesting objects do not solve every mystery. They sharpen the questions. Another famous mystery involving voids is the CMB cold spot. The cosmic microwave background is mostly consistent with the Standard Model. Its tiny fluctuations match the predictions of an early universe seeded by quantum fluctuations and shaped by inflation. But some features have drawn attention because they appear unusual. One of them is a large region of the microwave sky that is colder than average, known as the cold spot. One proposed explanation is a supervoid along the line of sight. The idea involves the integrated Sachs-Wolf effect. When a photon passes through a gravitational potential, its energy can change. In a universe where gravitational potentials evolve over time, especially because of dark energy, photons crossing large structures or voids can gain or lose a tiny amount of energy. A large void could leave a subtle cold imprint on the cosmic microwave background. In the direction of the cold spot lies the Eridanus supervoid, an enormous underdense region. Observations have found that this region contains fewer galaxies and less matter than surrounding regions. It is one of the largest known underdensities in our cosmic neighborhood. But does it explain the cold spot? The honest answer is complicated. The Eridanus supervoid may contribute to the temperature anomaly. It appears to be aligned with the cold spot and may leave an imprint through the integrated Sachs-Wolf effect. But current evidence does not prove that it fully explains the anomaly. Some analyses suggest the effect is too small. Others argue the connection is significant but not sufficient. The cold spot may be a rare statistical fluctuation in the primordial cosmic microwave background. It may be partly caused by a supervoid, or it may point to something not yet understood. The mystery remains. And that is more powerful than a false certainty. A documentary about voids must resist exaggeration. The real universe is already astonishing. We do not need to turn every underdensity into a portal, every anomaly into proof of another universe, or every supervoid into a violation of physics. The truth is stranger because it is measurable. A supervoid can be real and still not explain everything. A cosmic anomaly can be fascinating and still be a statistical accident. A theory can be successful and still incomplete. The voids teach humility. They are immense, but they are subtle. They are dramatic, but they do not announce themselves. They are discovered through absence, through statistics, through the missing galaxies in a map and the faint bending of light from objects behind them. To find a void, astronomers must first find what is not there. This makes voids different from most astronomical objects. A star is a source. A galaxy is a source. A black hole can reveal itself through accretion, jets, or the motion of nearby matter. A supernova announces itself with a flash. A pulsar beats. A quasar blazes. A void whispers. It appears when the expected number of galaxies fails to arrive. It is a pattern in silence. Yet that silence covers most of the volume of the universe. Most galaxies live in filaments and walls, but much of cosmic space belongs to voids. The universe by volume is dominated not by crowded clusters, but by underdense regions. The grand visual beauty of astronomy often comes from the bright objects, but the large-scale geometry of the universe is equally governed by the dark spaces between them. There is a deep lesson here. The universe is not made only of things, it is made of relationships. A galaxy cluster is meaningful because it is denser than its surroundings. A void is meaningful because it is emptier than its surroundings. Structure is contrast. The cosmic web is a pattern of highs and lows, peaks and basins, knots and gaps. Without contrast, the universe would be smooth, and a smooth universe would be sterile. The existence of voids is part of the reason anything exists at all. Because the same primordial fluctuations that created underdense regions also created overdense regions. Without the early unevenness, matter would not have collapsed into stars. Without stars, there would be no heavy elements. Without heavy elements, no rocky planets. Without planets, no oceans, no chemistry, no life. The emptiness and the light have the same origin. The voids are siblings of the galaxies. To follow that origin more deeply, we must consider inflation. Inflation is the theory that, in a tiny fraction of a second after the beginning of the observable universe, space expanded at an extraordinary rate. This rapid expansion could explain why the universe is so uniform on large scales, why space appears nearly flat, and why regions far apart in the sky have nearly the same temperature. Inflation also provides a mechanism for the tiny initial fluctuations. Quantum fluctuations, stretched to cosmic scales, became differences in density. Later, gravity amplified them. This idea is powerful, but not complete. There are many models of inflation. Scientists still debate its exact nature, its energy scale, and how it began or ended. But the broad picture, that tiny early fluctuations grew into large-scale structure, is central to modern cosmology. In that picture, voids are fossil evidence. They are expanded, evolved descendants of primordial underdensities. They are ancient signatures written across billions of years. The matter we see today has been moving under gravity for almost the entire history of the universe. But the pattern was seeded at the beginning. When we map voids now, we are reading a late chapter of a story whose first lines are written in the cosmic microwave background. This is why voids connect the smallest and largest scales. Quantum fluctuations may have helped seed them. Dark matter helped shape them. Dark energy affects their growth. Galaxies reveal their boundaries. Weak lensing maps their missing mass. The cosmic microwave background may carry their imprints. A void is not an isolated topic. It is a meeting point for almost every major idea in cosmology. Even the word nothing becomes unstable when we study them. In physics, empty space is not simple nothingness. Quantum fields exist everywhere. Vacuum energy may be connected to dark energy. Particles and radiation pass through intergalactic space. Neutrinos stream across the cosmos. Gravitational waves ripple through space-time. Magnetic fields may thread the cosmic web in faint and difficult-to-measure ways. A cosmic void is empty only in the sense that it contains less matter. It is still part of the universe. It still expands. It still has gravity. It still carries information. It still participates in cosmic history. Inside the deepest voids, matter is rare, but time is not. Light crosses them. Particles pass through them. The expansion of space stretches across them. A galaxy inside a void still forms stars, ages, evolves, and dies. A supermassive black hole in a void galaxy may still feed. Supernovae may still enrich surrounding gas. Planets may still form. Even in a void, the universe continues. But at a different pace. In dense environments, galaxies are transformed by crowds. In voids, galaxies may preserve more of their original gas. They may form stars steadily rather than in bursts caused by collisions. They may have fewer mergers. They may remain smaller and more disk-like. Yet voids are not perfectly quiet. They contain faint filaments and small groups. Matter still flows. Structure still exists, only at lower density. This has changed how astronomers think about voids. They are not empty bubbles with nothing inside. They are complex ecosystems of low-density structure. Modern observations show that voids can contain tenuous internal networks, small filaments, dwarf galaxies, gas, and dark matter halos. The cosmic web continues inside the voids, but in miniature and at lower contrast. The void is not the end of structure. It is structure in its most delicate form. This matters for galaxy formation. The smallest galaxies are hard to observe. Many may be faint, diffuse, and dominated by dark matter. In voids, where the background is less crowded, such galaxies could help test theories of how dark matter halos form and how ordinary matter turns into stars. If simulations predict more small halos than observed, voids may help reveal whether the issue lies in dark matter physics, star formation, feedback from supernovae, or observational limits. Voids are quiet, but they are not simple. They are clean laboratories, but not empty test tubes. They hold clues to dark matter on small scales and dark energy on large scales. The idea of the cosmic web itself came from both observation and simulation. In computer models, scientists begin with initial conditions based on the early universe. They include dark matter, ordinary matter, gravity, and expansion. As the simulation evolves, a web naturally appears. Matter collapses first into sheets, then filaments, then halos. Voids expand between them. The simulated universe begins almost smooth. Then, gravity writes complexity. When simulations are compared with real galaxy surveys, the resemblance is striking. This does not mean every detail is solved, but it shows that the basic framework is powerful. The cosmic web is not an accident. It is what gravity does to a nearly smooth expanding universe with small initial fluctuations in dark matter. Voids are therefore not rare defects. They are expected outcomes. Their size distribution, abundance, shapes, and evolution can be predicted statistically. If observations match those predictions, confidence in the model grows. If they do not, scientists look for missing ingredients. Perhaps dark energy evolves. Perhaps gravity differs on large scales. Perhaps neutrino masses affect the growth of structure. Perhaps dark matter is not perfectly cold. Perhaps galaxy formation biases the way we trace the underlying matter. Every void is part of this test. A single void may be interesting. A catalogue of thousands of voids becomes cosmology. This is why survey design matters. To find voids reliably, astronomers need large volumes, accurate redshifts, well-understood selection effects, and careful algorithms. If a survey misses faint galaxies, a region may appear emptier than it is. If distance estimates are uncertain, structures can blur. If the survey footprint has gaps, artificial voids may appear. If dust in the Milky Way blocks part of the sky, galaxy counts can be distorted. The universe is hard to map because we are inside it. We cannot step outside and photograph the whole cosmic web. We observe from one location through our own galaxy with instruments that have limits. We reconstruct the pattern from light arriving at Earth after traveling for millions or billions of years. And because light takes time to travel, every cosmic map is also a time map. A distant galaxy is seen as it was in the past. A galaxy 1 billion light-years away is seen roughly 1 billion years ago. A galaxy 10 billion light-years away is seen when the universe was much younger. Large surveys do not show the universe at one single moment. They show a layered history. Voids, too, are observed across time. Nearby voids show the relatively recent universe. Distant voids show earlier stages of cosmic structure. By comparing them, astronomers can study how voids evolve. In general, voids grow and become emptier with cosmic time, while dense structures become more pronounced. The cosmic web ages. Its knots tighten, its filaments sharpen, its voids deepen. Dark energy changes the story. For the first several billion years, matter played the dominant role in slowing cosmic expansion and growing structure. But later, dark energy became increasingly important. The expansion of the universe began accelerating. This affects how structures grow. Gravity still pulls matter together locally, but cosmic acceleration makes it harder for new large structures to collapse. Voids are especially sensitive to this shift because they are regions where expansion dominates over gravitational collapse. Their growth history may help reveal whether dark energy is truly constant or changes over time. This is one of the great questions of modern cosmology. Is dark energy a cosmological constant built into space itself? Is it a dynamic field that evolves? Is it a sign that gravity must be modified? Or is our interpretation missing something deeper? Voids cannot answer alone, but they are part of the evidence. The baryon acoustic oscillation signal is another part of the story. Before the cosmic microwave background was released, the early universe contained waves moving through the hot plasma of matter and radiation. These sound waves left a preferred scale in the distribution of matter. After the universe became transparent, the waves stopped propagating, but their imprint remained. Today, that imprint appears as a subtle statistical preference for galaxies to be separated by a particular distance. This scale acts like a cosmic ruler. By measuring it at different distances, astronomers can trace how the universe has expanded over time. DESI and other surveys use this technique to study dark energy. Voids are related because the same large-scale distribution of matter that contains the baryon acoustic oscillation signal also contains the cosmic web of clusters, filaments, walls, and voids. The universe remembers sound in its structure. It remembers quantum fluctuations in its web. It remembers dark energy in its expansion. Voids are part of that memory. When we speak of supervoids, we enter the edge of what is statistically rare. The observable universe is huge, so rare structures can exist. A supervoid hundreds of millions or more than a billion light-years across sounds almost impossible by human standards. But cosmology asks a different question. Given the size of the observable universe and the rules of structure formation, how likely is such a feature? This is where intuition often fails. A structure can be enormous and still be allowed. A feature can be unusual and still not break the standard model. A void can be one of the largest known things and still be part of the expected cosmic distribution. But some structures challenge models more than others. When astronomers find very large walls, superclusters, quasar groups, or voids, they ask whether these are true coherent structures, chance alignments, survey artifacts, or statistically expected extremes. Not every claimed giant structure has the same status. Some are robust, some are debated, some depend strongly on definition. The cosmological principle says that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means roughly the same from place to place. Isotropic means roughly the same in every direction. This does not mean the universe is smooth on all scales. Galaxies, clusters, and voids clearly exist. It means that if we average over large enough volumes, the universe approaches uniformity. Voids test this principle. If structures became too large or too extreme, They might challenge our assumption that the universe smooths out on the largest scales. So far, the standard model remains broadly successful, but the debate over the largest structures continues. It is not only about cataloging cosmic giants. It is about whether our deepest assumption about the universe is correct. Are we seeing a fair sample of the cosmos? Is our location ordinary? Does the universe average out as expected? Voids help answer these questions because they are the largest underdense structures we can observe. They are the negative image of cosmic clustering. They tell us how uneven the universe can be. They also affect how we think about time and fate. The universe is expanding, and that expansion is accelerating. Over extremely long timescales, distant galaxies beyond our gravitationally bound neighborhood will move farther away. Their light will be stretched. Some will become unobservable beyond cosmic horizons. Future observers in the far distant universe may see a much emptier sky. In a sense, the universe itself is becoming more void-like at the largest observable scales. Not because matter disappears locally, but because cosmic acceleration isolates gravitationally bound islands from one another. Galaxy groups and clusters that are bound will remain together. Everything beyond will recede increasingly beyond reach. The future universe may be a collection of lonely islands separated by expanding darkness. Voids, then, are not only present structures, they may foreshadow the long-term cosmic future. But we should be careful. On human timescales, galaxies and voids are essentially frozen. A void, hundreds of millions of light-years across, does not visibly change in a century. Cosmological evolution happens over billions of years. We infer it by looking across distance and time, not by watching a single void evolve in real time. Astronomy is archaeology with light. We dig by looking outward. The deeper we look, the older the universe becomes. The cosmic web has another important ingredient: ordinary matter outside galaxies. Not all ordinary matter is locked in stars. Much of it exists as gas between galaxies in the circumgalactic and intergalactic medium. Some of this gas is hot and diffuse. Some is difficult to detect. Astronomers have long worked to account for the universe's baryons, the ordinary matter made of protons, neutrons, and electrons. Voids may contain very thin gas, but much of the missing ordinary matter is expected in the warm, hot intergalactic medium, especially along filaments. The boundaries of voids, where matter has flowed and accumulated, may hold significant gas reservoirs. By studying absorption lines in the spectra of distant quasars, scientists can detect gas that would otherwise be invisible. A quasar is an intensely bright, active galactic nucleus powered by a supermassive black hole. As quasar light travels through the universe, intervening gas absorbs specific wavelengths. These absorption features reveal the presence of hydrogen, metals, and ionized gas across cosmic distances. In this way, a quasar becomes a flashlight shining through the cosmic web. Its spectrum carries shadows of matter between galaxies. Some of those shadows trace filaments. Some help map the edges of voids. Again, absence is studied through light. The cosmic web is not only a galaxy map, it is a matter map, a gas map, a dark matter map, a history map. Galaxies are bright signposts, but they do not contain the whole story. Inside voids, the lack of galaxies does not mean the absence of physics. It means the physical processes happen in a thinner, quieter environment. Gas may be too diffuse to form many stars. Dark matter halos may be too small to gather enough ordinary matter. Ultraviolet radiation from stars and quasars may prevent gas in small halos from cooling. Supernova feedback may expel gas from dwarf galaxies. Many factors decide whether a dark matter halo becomes visible. This is why voids can test galaxy formation models. If simulations predict many small galaxies in voids, but surveys find fewer, scientists must ask why. Are the galaxies too faint to see? Did feedback suppress star formation? Is dark matter different from what we think? Did reionization heat the gas and prevent small galaxies from forming? The emptiness of a void may reveal the physics of the faintest galaxies. Even black holes may be connected to the story. Supermassive black holes at the centers of galaxies can launch jets that extend far beyond their host galaxies. Some radio jets are enormous, affecting gas across intergalactic distances. On the scale of the cosmic web, energetic feedback from galaxies and black holes may influence how gas moves, heats, and forms stars. The role of such feedback in the larger structures is still an active field of research. Black holes do not create cosmic voids in the usual sense. A common misconception is that voids are caused by black holes swallowing matter. They are not. Even the largest black holes affect only tiny regions compared with cosmic voids. A supermassive black hole may dominate the center of a galaxy. A cosmic void spans millions to hundreds of millions of light years. The scale difference is enormous. Voids are not made by black holes. They are made by cosmic expansion, gravity, dark matter, and the initial conditions of the universe. Another misconception is that voids are dangerous emptiness, like cosmic pits that objects might fall into. In reality, a void is not a hole in space-time. It is simply a region with lower density. A spacecraft entering a void would not encounter a boundary. There would be no wall, no sudden drop, no edge. The stars and galaxies would gradually become fewer. The distances between luminous objects would grow larger. The background darkness would deepen. The void would not announce itself, only a map would reveal it. This is one of the hardest things to visualize. Human senses evolved for nearby objects, edges, surfaces, and motion. Cosmic voids have none of these in an immediate way. Their reality is statistical and spatial. You cannot stand at the edge of one and look down. You cannot see its surface. You can only reconstruct it from the positions and motions of galaxies across vast distances. The void is an object made of context. It exists because of the pattern around it. This makes it strangely modern. Voids are not objects in the old astronomical sense. They are structures in data. They require surveys, computation, statistical definitions, simulations, and theory. They are among the clearest examples of how astronomy has changed, from observing isolated wonders to mapping the universe as a whole. A telescope once revealed a moon around Jupiter. Now, telescopes reveal the geometry of cosmic history, yet the emotional power remains. To contemplate a void is to confront scale in its purest form. Not the scale of something huge, like a galaxy cluster or black hole, but the scale of almost nothing. A region where millions of galaxies could have been, but are not. A silence so large that it becomes a structure. The universe is extravagant not only in what it creates, but in what it leaves empty. One of the great void-related discoveries is that our own Milky Way sits near a local underdense region called the local void. It is not the largest void, but it affects the motion of nearby galaxies. Our local group is influenced by the gravity of surrounding structures and by the relative lack of matter in nearby empty regions. Galaxies appear to flow away from the local void and toward denser concentrations such as the Virgo cluster and the Great Attractor region. This reminds us that voids are not distant curiosities. They are part of our neighborhood. The Milky Way is not floating in a random dark sea. It belongs to a cosmic environment with nearby groups, clusters, filaments, walls, and underdense regions. Our galaxy's motion through the universe reflects that environment. We are pulled by the dense and, in a relative sense, pushed away from the empty. Strictly speaking, voids do not push through a new force. There is no anti-gravity coming from a void in ordinary structure formation. The effect arises because matter is distributed unevenly. Dense regions pull more strongly than underdense regions. Compared with a uniform background, a void acts like a region of missing gravitational pull. The result can look like motion away from emptiness. Even absence has gravitational consequences. That phrase sounds poetic, but it is physically meaningful. A region with less mass than average affects the gravitational field differently from a region with average density. The missing matter matters. This is why voids are useful for understanding cosmic flows. Galaxies move in response to the entire surrounding density field. By mapping both overdensities and underdensities, astronomers can reconstruct the gravitational landscape of the nearby universe. The universe is not only expanding, it is flowing. On small scales, galaxies orbit, fall, merge, and drift. On larger scales, clusters pull matter inward, while voids expand outward. On the larger scales, the expansion of the universe dominates. The observed motion of any galaxy is a combination of cosmic expansion and local gravitational motion. Voids help separate these effects. They also raise one of the deepest questions in cosmology. What does it mean to measure the expansion of an uneven universe? The simplest cosmological models assume a smooth average universe. This is not because scientists think galaxies and voids do not exist. It is because, on large enough scales, the universe appears statistically uniform. The equations describe the average expansion. Then smaller scale structures are treated as perturbations. But some researchers study whether the clumpiness of the universe, including voids and clusters, could subtly affect the interpretation of cosmic expansion. This is called back-reaction in some contexts. Most mainstream analyses find that these effects are not large enough to replace dark energy, but the question is subtle. It touches the foundation of how we average an inhomogeneous universe. Voids force us to ask, when we say the universe expands, whose universe are we averaging? The answer is not simple, but the standard model remains highly successful. It has survived many tests because it connects many independent observations: the cosmic microwave background, galaxy clustering, baryon acoustic oscillations, supernova distances, weak lensing, light element abundances, and the ages of stars. Voids must fit into that web of evidence. A theory that explains voids but breaks the cosmic microwave background is not enough. A theory that changes gravity in voids must also explain galaxies, clusters, lensing, and gravitational waves. Cosmology is a network of constraints. The voids are one thread, but a crucial one. They are especially interesting because they are low-density regions. Some modified gravity theories include screening mechanisms that hide deviations from general relativity in dense environments, like the solar system, but allow them to appear in emptier regions. If such theories are correct, voids might show stronger deviations than clusters. This makes voids a weak field frontier. Black holes test gravity in extreme, strong fields. Voids test gravity in vast, weak fields. Both are essential. A complete theory of gravity must work near event horizons and across hundreds of millions of light-years of emptiness. It must describe the fall of an apple, the orbit of planets, the collision of black holes, the bending of light, and the expansion of voids. The universe tests its laws everywhere, even where almost nothing is. As surveys improve, void science becomes more precise. Astronomers can identify voids in galaxy distributions, reconstruct matter density fields, measure galaxy velocities, compare lensing signals, and study correlations with the cosmic microwave background. Machine learning and advanced simulations help classify structures and compare models. New datasets bring deeper maps, fainter galaxies, and larger volumes. But larger data does not remove the need for caution. Void catalogs depend on the galaxies used to trace them. A catalog made from bright galaxies may identify different voids from one made with faint galaxies. Photometric redshifts, which estimate distance from colors, are less precise than spectroscopic redshifts, which measure spectral lines. Survey masks and selection effects can mimic or obscure underdensities. To study nothing, one must understand every bias in seeing something. This is part of why voids are scientifically beautiful. They are simple in concept, but difficult in practice. Everyone understands a region with fewer galaxies, but measuring it rigorously requires sophisticated mathematics. There are several ways to define voids. Some methods look for empty spheres. Others use watershed algorithms, imagining the density field like a landscape where basins drain into minima. Others identify underdense regions based on smoothed density thresholds. Each method captures a different aspect of void structure. No single definition is perfect. The best choice depends on the scientific question. For galaxy evolution, one may care about whether a galaxy lives in a low-density environment. For cosmology, one may care about the shape, size, and lensing profile of voids. For the integrated Sachs-Wolf effect, one may care about very large supervoids aligned with the cosmic microwave background. For testing gravity, one may care about velocity profiles and density contrasts. A void is not one thing to all scientists. It is a family of related structures. This complexity should not weaken our sense of wonder. It should deepen it. The fact that emptiness can be classified in different ways means it has richness. It is not blank. It has profiles, substructures, dynamics, and connections. The center of a void is usually the most underdense region. Moving outward, density tends to rise. At the boundary, there may be a ridge or wall where galaxies are more common. Some voids are surrounded by dense shells. Others open into neighboring underdensities. Some are embedded in complex environments. Voids can merge. As the universe evolves, smaller voids can combine into larger ones. Dense walls between them may thin or be absorbed into the surrounding structure. This hierarchical evolution means voids have family histories. They are not static holes, but growing regions shaped by the flow of matter. In simulations, voids often expand and become rounder in their interiors, though surrounding tidal forces can distort them. Their shapes carry information about the cosmic density field and the laws of gravity. If the universe expands uniformly, voids should not have a preferred orientation on average. But observational effects in cosmology can distort their apparent shapes. This leads to another test, the Alcock-Pazensky effect. If we assume the wrong cosmological model when converting redshifts and angles into distances, spherical objects or statistically isotropic structures may appear stretched or squashed. Voids can be used in this way. Their apparent shapes contest the relationship between distance and redshift, helping constrain cosmic expansion. Again, emptiness becomes a ruler. A void can be a laboratory, a lens, a clock, a ruler, and a test of gravity. It is one of the most versatile structures in cosmology, precisely because it is so large and so underdense. And yet, to the eye, it is almost nothing. This contrast is at the heart of the documentary. We are drawn to light. But the universe's largest messages may be written in darkness. The story also has a human dimension. The discovery of voids changed our cosmic self-image. At first, humans placed Earth at the center, then the Sun, then the Milky Way. Each step outward displaced us. The discovery of galaxies revealed a universe far larger than the Milky Way. The discovery of the cosmic web revealed that even galaxies are not the main units of structure. They are beads on threads, sparks along filaments, traces of something larger. And voids revealed that the largest features may be absences. This is a profound reversal. Ancient astronomy was about lights in the sky. Modern cosmology is also about the darkness between lights. In that darkness, the universe becomes comprehensible. The cosmic web is often compared to a sponge, foam, or neural network. These analogies are useful but imperfect. A sponge has solid material and holes. The cosmic web has matter and underdensity, but no solid surfaces. Foam has bubbles with walls. The cosmic web has filaments and voids, but the boundaries are gravitational and statistical. A neural network has signals and cells. The cosmic web has no purpose or thought. Still, the visual resemblance is striking. Nature often produces networks through simple rules: growth, flow, attraction, pressure, constraint. The cosmic web emerges from gravity and expansion. Its beauty is not designed, it is the result of physical law acting over time. Voids are the negative spaces of that law. When artists create an image, negative space can be as important as the subject. It guides the eye, it defines form, it gives balance. In the universe, voids play a similar role. They define the web by their absence. They make the filaments visible as boundaries. They turn a collection of galaxies into architecture. Without voids, the universe would be a fog. With voids, it becomes a web. The largest voids also challenge language. Words like large, empty, distant, and ancient become inadequate. A supervoid, 1 billion light-years across, is not just big, it is a scale beyond ordinary comparison. If light entered one side when complex life was beginning to flourish on Earth, it might still not have crossed by the time humans appeared. A human lifetime is too short to see such a structure change. A civilization's recorded history is too short. Even the age of mammals is small compared with the crossing time of the largest cosmic structures. The universe is not only bigger than we imagine, it is bigger than our categories of imagination. Yet mathematics lets us hold it. A redshift, a density contrast, a correlation function, a lensing profile, a power spectrum. These are the handles by which the mind grasps the void. Science does not remove wonder. It gives wonder a skeleton. Nowhere is that clearer than in the relationship between voids and the cosmic microwave background. The oldest light passes through the later cosmic web before reaching us. Along the way, it encounters clusters, filaments, and voids. These structures can lens it, shift it, and imprint subtle secondary patterns. The cosmic microwave background is therefore both a picture of the early universe and a screen behind the later universe. Voids may leave faint shadows on that screen. The integrated Sachs-Wolf effect is one such shadow. Gravitational lensing is another. The Sunyaev-Zeldovich effect, caused when CMB photons scatter from hot electrons in galaxy clusters, is mainly associated with dense regions. But it is part of the same broader idea. The ancient light carries marks of everything it passes. The universe is layered. Early fluctuations become latest structures. Latest structures alter early light. We observe the combination and work backward. This is cosmology, the art of untangling time. Supervoids are especially tempting because they seem capable of connecting the largest structures with the oldest light. The Eridanus supervoid and the cold spot are the most famous example. But there may be many supervoids whose effects are subtle. By stacking the CMB signal around many voids and superclusters, scientists search for the average imprint of cosmic structure. These measurements are difficult. The expected temperature shifts are tiny. Foregrounds from our own galaxy, radio sources, dust, and survey systematics must be controlled. Statistical choices matter, but the effort is worthwhile because it tests dark energy and the evolution of gravitational potentials. A void's shadow on the CMB is not just a curiosity. It is evidence that the expansion history of the universe affects light. In a universe without dark energy, the gravitational potentials associated with large structures would evolve differently. the integrated Sachs-Wolf effect would be different. Thus, the faint temperature imprint of voids and superclusters becomes part of the evidence for cosmic acceleration. The emptier structures help reveal the force driving the universe apart. But again, language can mislead. Dark energy is not a force in the everyday sense. It is a name for whatever causes the accelerated expansion. In the simplest model, it is the energy density of empty space itself, constant in time and uniform in space. But whether that is the final explanation remains unknown. The voids are where this mystery feels almost tangible. If empty space has energy, then the emptiest regions of the universe are not empty in the deepest physical sense. The void becomes a stage on which the nature of space itself matters. What is space when matter is almost absent? Does vacuum energy truly remain constant? Does gravity respond to it exactly as Einstein's equations predict? Are cosmic voids simply underdense regions in matter, or are they also windows into the physics of the vacuum? These are not settled questions. They are frontiers. A good documentary does not need to pretend we know more than we do. The unknown is part of the structure. We know voids exist. We know they arise naturally from gravitational evolution. We know they occupy enormous cosmic volumes. We know they contain fewer galaxies and less matter than average. We know they influence galaxy evolution, cosmic flows, lensing, and microwave background signals. We know they can test cosmology, but we do not know everything. We do not know the true nature of dark matter. We do not know the true nature of dark energy. We do not know whether the Hubble tension is new physics or unresolved systematics. We do not know whether every large cosmic anomaly is chance, structure, or a clue. The voids sit inside these unknowns. They are not blank spaces in knowledge. They are active borders of knowledge. Consider what it means to map a void. A telescope records light from galaxies. Each galaxy's spectrum reveals a redshift. Redshift gives distance. Distances create a three-dimensional distribution. Algorithms search that distribution for underdense basins. Simulations predict how many such basins should exist. Lensing checks the matter content. Galaxy properties reveal environmental effects. CMB comparisons search for temperature imprints. A void is discovered through a chain of inference. Every link matters. And yet the final image is simple. Here, the universe made less. The simplicity is earned. The Boötes Void, the local void, the Eridanus supervoid, and countless smaller voids in survey catalogs are not isolated curiosities. They are pieces of a cosmic pattern. The names help us talk about them, but the real subject is the void population as a whole. Just as biologists learn from ecosystems, cosmologists learn from populations. One galaxy can be unusual, millions reveal laws. One void can be rare, thousands reveal cosmology. With modern surveys, the number of known voids has grown dramatically. Different catalogs identify voids across different redshift ranges and tracer populations. Some are nearby and detailed, others are distant and statistical. The more complete the maps become, the more voids can be used alongside galaxies, clusters, supernovae, and the CMB to constrain the universe's history. This is the new era of void cosmology. For decades, voids were mostly visual evidence of the cosmic web. They showed that the universe had structure on enormous scales. Now, they are becoming quantitative probes. Their importance is rising because our questions are becoming more precise. The question is no longer only, what does the universe look like? It is, which theory produces this exact pattern of emptiness? That is a much harder question, and it may lead beyond the standard model. Some alternative theories try to explain cosmic acceleration without dark energy by modifying gravity. Others introduce evolving dark energy fields. Others explore interactions in the dark sector, where dark matter and dark energy might not be entirely separate. Still others investigate whether early dark energy could help resolve the Hubble tension. Voids can help test these ideas because they respond to both geometry and growth. Geometry tells us how distances relate to redshift. Growth tells us how matter clumps over time. A theory must match both. A universe may expand in a certain way, but structures may grow differently. Voids feel both effects. Their shapes probe geometry. Their abundance and density profiles probe growth. Their velocities probe gravity. Their lensing probes mass. Their galaxies probe formation physics. Few cosmic structures offer so many tests at once. This is why emptiness is becoming crowded with meaning. Imagine a future map of the universe, not as a flat image, but as a navigable three-dimensional ocean of galaxies. We move through luminous filaments stretching across billions of light years. We pass clusters where thousands of galaxies crowd together. Then we enter a void. The galaxies thin. The web recedes to the edges. Distances grow. The light becomes sparse. But the data does not vanish. The void has a density profile, a velocity field, a lensing signature, a shape, a history, a relationship to nearby filaments, a place in the statistics of the cosmos. We are flying through a measurement. The emptiness is legible. That may be the central revelation. The universe is not divided into meaningful objects and meaningless gaps. The gaps are meaningful. The large-scale structure is a pattern of matter and missing matter together. To understand one, we need the other. The Milky Way itself exists because matter gathered into a dark matter halo, gas cooled, stars formed, and generations of stellar life produced heavy elements. But that gathering happened within a cosmic environment shaped by the evacuation of surrounding regions. The material that did not remain in voids helped build the structures where galaxies live. The atoms in our bodies were forged in stars, but the cosmic conditions that allowed stars to form were born from a universe that became uneven. We are made of matter that fell out of the voids, not literally from one named void, but from the same cosmic process. Matter flowed away from underdense regions and into denser ones. Those denser regions eventually made galaxies. Galaxies made stars. Stars made elements. Elements made planets. On at least one planet, matter became aware of the universe. The voids are part of our ancestry. This is not mysticism. It is structure formation. The existence of life depends on the universe not being smooth. A perfectly even universe would be lifeless. The voids and galaxies are both consequences of the unevenness that made complexity possible. So when we look into a cosmic void, we are not looking at failure. We are looking at one half of creation, the half that gave the other half room to form. The largest voids also remind us that the universe has no obligation to fill itself. Human imagination often expects purpose, balance, or fullness. But the universe is governed by laws and initial conditions. Matter gathers where gravity guides it. Space expands. Radiation cools. Structures form. Voids deepen. The result is not designed for us, and yet we can understand it. That may be the most astonishing fact of all. A species on a small planet, orbiting an ordinary star, in one galaxy among billions, can build instruments capable of mapping the distribution of matter across cosmic time. We can identify regions hundreds of millions of light years wide where galaxies are missing. We can compare them with simulations. We can use them to test dark energy. We are tiny, but not blind. The voids are enormous, but not unknowable. Their discovery was not a single moment, but a gradual unveiling. Early redshift surveys showed hints. Larger surveys revealed walls and gaps. Simulations gave theoretical context. Microwave background observations connected structure to the early universe. Weak lensing added invisible mass. Modern surveys are turning the picture into precision cosmology. The story is still unfolding. DESI continues to extend the three-dimensional map of galaxies and quasars. Euclid is building a deep view of the dark universe. Rubin will add time, depth, and scale. Future radio surveys may map hydrogen across vast distances. Next-generation CMB experiments may improve measurements of lensing and secondary anisotropies. Together, they will show voids with greater clarity than ever before. The coming maps will not simply contain more galaxies, they will contain better emptiness, sharper voids, deeper statistics, more accurate tests. The more we see, the more the voids will speak. Perhaps they will confirm the standard cosmological model with greater precision. Perhaps they will reveal subtle deviations. Perhaps they will help explain tensions in current data. Perhaps they will show that dark energy is constant. Perhaps they will show that it evolves. Perhaps they will rule out modified gravity models. Perhaps they will support one. The voids are waiting as evidence, not as answers we can choose, but as reality we must measure. In the end, a cosmic void is a paradox. It is one of the largest things in the universe, defined by having less of almost everything. It is a structure of absence, a presence made from scarcity, a region that teaches us about matter by lacking it. It is easy to be moved by stars. They shine directly into our eyes. Voids require another kind of vision. They ask us to see statistically, gravitationally, historically. They ask us to recognize that the universe is shaped as much by what has moved away as by what has gathered. They ask us to accept that emptiness can have architecture. And once we see that, the cosmos changes. The darkness between galaxies is no longer background. It is part of the story. The voids are not the places where the universe stopped building. They are the places that reveal how the building happened. From tiny fluctuations in the early fireball, through the pull of dark matter and the flow of gravity, through billions of years of expansion, the universe became a web. Galaxies lit the threads. Clusters marked the knots. Walls rose across space, and the voids opened between them. Silent, immense, evolving, measurable. They are the great dark rooms of the cosmos, and in their emptiness, they hold the shape of everything.